Hello, everybody, and welcome to BioSC 140 Human Physiology. This video is going to cover S4P2 Part 3. We're going to finish up the respiratory system lectures in this video. So, the vast majority of oxygen is carried inside red blood cells. Well, let's review. What does the respiratory system do? There were a few distinct things that we talked about early on in the lecture. Gas exchange, pH balance, immunity, and what I'm doing right now, vocalization, are the four primary jobs of the respiratory system. So, transporting oxygen, well, that helps a lot with the first one, with the gas exchange, getting oxygen to where it needs to be job. So let's look at this. We've seen this before with our cardiovascular lectures. 97% of oxygen is carried by hemoglobin inside of red blood cells as oxyhemoglobin. It binds to the iron in the heme group in the hemoglobin molecules. There are 4 heme groups per hemoglobin molecule, so 4 oxygens per molecule. Oxygen, O2, is not very soluble in water. It's got low solubility in water, so only about 3% is just freely dissolved in our liquid blood, our aqueous medium. This soluble O2, the O2 that's dissolved in our blood, that's what our chemoreceptors can detect. Our chemoreceptors don't detect hemoglobin saturation. They detect the dissolved oxygen. So carbon dioxide, its deadliness, its lethality is increased because of this. There's no respiratory compensation because our bodies still, for too long, detect normal oxygen levels, even though our hemoglobin is carrying less oxygen. So carbon monoxide, remember, it's tasteless, it's odorless, it's colorless, it's smellless. You got to have a carbon monoxide detector in order to detect carbon monoxide, CO. All right, let's move on. So carbon monoxide is very dangerous. It competitively binds to hemoglobin, and when carbon monoxide binds to hemoglobin, it binds very tightly. It has a very high affinity, and it doesn't come off easily. So that decreases our blood's carrying capacity for O2. Carbon dioxide, if we go back to our respiratory system, carbon dioxide is involved in the gas exchange part of what it does, and also the pH balance part. 70% of carbon dioxide, when it's dissolved in our blood, is converted to carbonic acid, which dissociates and gives us a hydrogen ion and bicarbonate. 7% is dissolved in our bloodstream, in plasma, and about 23% is carried by hemoglobin as carbaminohemoglobin. It binds to an amino acid within our hemoglobin. Respirometers measure the air moved during breathing. So we experience this in lab. So you've seen this chart also. If you haven't seen it in lab, you will see it in lab. So what this chart represents is volume. So if we measure from the bottom line to the very top, that's our total lung capacity. total lung capacity. There's different names for different types of breathing, different volume changes in our lungs. Tidal volume, TV, is the volume of air moved during a single respiratory cycle. It's usually around 500 milliliters at rest, but it ultimately depends on size. And this tidal volume increases during exercise. So tidal volume's right here. And what you can see is during normal breathing, we don't exhale 100% of the air out of our lungs. There's still a large amount that's still inside of our lungs as we exhale. And when we inhale, we don't inhale as much as we possibly can. We still have a large ability to increase it more. Respiratory rate, or RR, is the total number of breaths in a given period of time. Vital capacity is the maximum volume that can be voluntarily moved in one breath. Vital capacity, maximum amount can be voluntarily moved in one breath. So a full exhale bring us down to here. I do want you to note that even with full exhale, there's still some air left in our lungs, this residual volume down here, residual volume. So this is max exhale. There's still some volume of air in our lungs. Vital capacity is from that to full inhale, right here, full inhale. That's vital capacity. Minute ventilation refers to the volume of air moved moved during a given time. Volume of air moved during a given time. So we can calculate tidal volume with a respirometer. We can calculate respiratory rate. With those two variables, we can combine them. So respiratory rate, how many breaths per minute? Tidal volume, just normal breathing. It will give us the amount of air moved in a minute, our minute ventilation. Respiratory rate is number of breaths in a given time, typically per minute, so 12 to 20 per minute. So, I want you to do a thought experiment. When exercising, is it more efficient? Is it better to breathe more often to increase respiratory rate, or to breathe more deeply to increase your minute ventilation? So you have your minute ventilation at rest. You're an athlete, you want to go exercise, and you want to ventilate your lungs as efficiently as possible. Is it better to focus on increasing your respiratory rate or increasing your tidal volume? Thought experiment. All right, let's move on. So minute ventilation, let's see. Let's take average numbers. So 12 breaths per minute, average respiratory rate, 500 milliliters, average tidal volume, 12 times 500 gives us 6,000 milliliters per minute as a average minute ventilation. Let's see what happens when we double the respiratory rate. Well, 24 times 500 gives us 12,000. Well, now let's double tidal volume. So 12 times 1,000 is 12,000. Look at this. The math is the exact same. So what do you think works better, increasing respiratory rate or increasing tidal volume? The math is the exact same if you double, comparing doubling respiratory rate or doubling tidal volume. Well, minute ventilation is not representative of the air that's available for exchange. Where does gas exchange happen? Gas exchange happens in the alveoli where the capillaries are, at that interface of the capillary and the alveoli. That's where gas exchange happens. So knowing that, how does this change the equation? Well, we've got to consider something called dead space. Dead space is airway volume with a reduced exchange capacity. So the trachea, the bronchi, and the smaller bronchi. The anatomical DS, or dead zone, is the conducting zone. It's the area where that's job is to just conduct and bring that air to our alveoli. This tissue is not capable of exchange. It's everything but these tiny bronchioles and alveoli. 99% of gas exchange happens in these alveoli. So how does that change this equation? All right, well, let's look at some other factors. Let's look at some other factors that we might need to consider. Well, anatomically, our lungs are not equal throughout. There are some differences in the physiology and the function, the characteristics of the different parts of our lungs. The top of our lungs, or the superior aspect of our lungs, tends to have more air and less blood. Gravity preferentially sends the blood to the lower parts of our lungs, which leads to more blood in the lower parts of our lungs and more air in the upper parts of our lungs. The bottom of our lungs, inferior, there's less air. Alveoli are more compressed by this blood. How does that affect this? Well, dead space can be affected by body weight, by the size of the person. We've got this term alveolar ventilation. Alveolar ventilation is referred to the volume of air reaching the alveoli in a given time. So you take out it's basically minute ventilation, but you remove the dead space volume. You remove the dead space volume. Dead space volume is roughly 150 milliliters. That's a good average number. So let's go back to our equation. We've got 12 breaths per minute respiratory rate times 500 minus 150 in the brackets. So tidal volume minus dead space. Well, that's going to give us 4,200 as our alveolar ventilation. Well, let's also take into consideration this idea over here of ventilation divided by perfusion ratio. So perfusion is blood flow to that tissue. So the ratio of air going in and out to perfusion. So AV is alveolar ventilation. Q is cardiac output. Typically, ventilation divided by perfusion ratio, alveolar ventilation divided by cardiac output, is typically about 0.8 to 0.9. Generally, we are a little overperfused. So let's move on. Is it better, knowing what we know now, when you're exercising, to increase respiratory rate or increase tidal volume? Well, let's see. If we double respirations, so we have 24 times 500 minus 150, gives us 8,400 is our alveolar ventilation. If we double tidal volume, this should be 12. 12 times the sum of 1,000 minus 150 gives us 10,200. 10,200. So it's actually better to increase tidal volume as opposed to respiratory rate when you're exercising. Now, increasing respiratory rate is going to help, but that's why when we work out, when we run, we tend to take deeper breaths, more so than faster increasing our breath rate. All right, everybody, that finishes up this lecture. As always, if there is anything I can do for you, just let me know. Send me an email with questions. I am here to help. Good luck studying for your test, and I will see you all in the next video.